Okay, thank you. Let me share the screen. Can you see my screen?
Yes.
Okay. So, yeah, please, when you have a question, please just ask because I don't know about the notification. They will show me the chats. All right. So, since we have full notes uploaded, so I will go briefly in the to the concepts only. I'm not going to write things as a whole uh, because it is there in the notes. It will save some times as well. All right. So today is 23rd. All right. So what do you think about integration? Right. So integration. Well, you have seen this notation in school, right? So what did you think of this when you saw this first notation? It must be very complicated, isn't it?
Area under the function from A to B.
Right. Right. So that is what geometric interpretation and right. So if f has some curve, something like this, then you have, so suppose this is A and let's say this is B. So you have the so this will be the value of this integration, this region, the area of this region. All right. Uh, well, in this case, of course, it is true, but one need a, well, see here. The point is, if you know that it is area of under the integral, area under under this curve, then why do we need a definition, right? Why do we need a proper definition and all this stuff using complicated stuff to go into the integration? So integration, see this integration is called Riemann integration, right? So Riemann was around 1840 to 50s. Around that time he was around, but integration was around even before that. All right. So integration was there, and people have thought like this, as you told. It is, you have a curve, and the curve is the graph of f. Then it is Integration is just the area under the curve. All right. But then there was certain problems. So, for example, uh, so around what year? Around the 1830s or something. Fourier came up with certain series which now called as Fourier series. So it was something like summation an uh, cos bn x plus uh, cos nx plus summation bn sin nx in from minus infinity to plus infinity actually. So yeah, it is true, but let's look at something like n belongs to z. N belongs to z, something like that. Came up with some kind of series and said that any function that any function can be expressed as the above series where n is something like there is, I think there is a constant 1 over 2 pi 2 pi possibly minus pi to pi fx, any function fx cos nx dx, cos nx, that is fine, cos nx dx, and bn is 1 over 2 pi. I think I'm correct, but I'll check it next time. Sin nx dx. So it's actually, of course, more generally, one would now say this should be written as some n e to the power I n x, n belongs to z, where an is integration 1 over 2 pi minus pi to pi fx e to the power minus I n x dx. Okay, so this is it. So one can do it using cos nx sin nx, and one can do this. But then for a general function, we knew that for a curve, for a graph, something like this, integration a to b fx dx is the area under the curve. But here Fourier said any function you can do it, right? Then question comes. So then, what is this integration? What is this integration then? Right? People didn't believe. because f might be any discontinuous function, right? Then what is the integration? The discontinuous function, there might be infinitely many discontinuities and so on. Who knows what? But then what is this integration? What is this integration? How does one make sense of this? Right. That was this was what? This was the question. The question that Riemann considered. So if you are interested, you can look at a book by Stephen Hawking, which is God Created the Integers. So you can look at that book, and there is actually biographies of several great mathematicians. One of them is Riemann, and he not just described in just the biography, he also translated few of his papers, and this paper is also got he translated it. So you can check out this paper, how he managed to think of this integration. That is quite intriguing.
Sir,
Yeah,
sir, this integration above it is coming from linear algebra. Yes.
linear algebra. How?
Sir, AN and BN one.
N and Bn are
Yes, sir.
numbers.
Definition, the integration we have for AN and BN.
Yes.
It's coming from linear algebra, right?
So which linear algebra? How?
No, sir, because in the previous linear algebra course, sir told that this is coming from linear algebra.
No,
But
I mean, this is coming from linear algebra. What does it mean? So, you see, what is vector space here?
yes, sir, he told that the cos and sine function they actually span space of continuous functions or something like that.
That is true, but it does not span as you are saying, right? These are not finite sum, right? You
Yes.
see, n belongs to z, so infinite sum. So, how do you make sense of spanning? So, you just not need to look at the span, but span closer. You need to look at closer of the span. So for that you need a concept of distance, which you already know. You can look at uniform norm and several things. So I'm not talking about convergence right here. So convergent of Fourier series is a big issue, which is already solved. And if those who are interested can look at it and can tell me, I'll suggest some material. The point is, yeah. So the later one can view that one from linear algebra point of view. Okay, so you look at cos nx and sin nx, and you look at the span. So span means finite sum, right? Finite linear combination, and look at collection of all those, right? Now, if you want to get from finite to infinite, you need to look at a sequence of it and look at limit, and that's where the analysis comes. Okay, so if it is finite sum, then it is fine, no problem. But any continuous function you cannot write as finite sum. That is not possible. Okay, so but the if you look at the vector space spanned by cos nx, sin nx, and look at its closure, it will be dense in continuous functions. Certain sense. Okay, that's what perhaps your linear algebra teacher told you. But Riemann's question was that time. I mean, people didn't believe that this kind of integration even exists. I mean, what the hell is this kind of integration? First of all, f can have many discontinuities. You may not get a curve. So that was the problem. So Riemann was this was the question that Riemann considered. Yeah, I had actually uh, uploaded the Riemann's paper last time. So if you're interested, I can do it this time as well. Okay, and you will see how Riemann thought about the integration. That is still in great context. So still it is in use. Okay, so and here we'll continue more about what Riemann has done, but let me now say in modern language what he did. So he considered actually. So he looked at first the continuous functions only. So right now, so suppose this is A and this is B, and well, this idea was not actually for Riemann's from Riemann's. This idea was there. So this idea was to partition this one small parts, right? So let's say this is suppose this is x naught, this is x1, x2, and this is xn equal to b. Okay, and then what one tries is we'll look at small portion. Right, and then try to find the area, a smaller one, each of them, and then add this up. Right now, so the point is now you divide, but then this one you one has to have certain things um, to find the area of the smaller part, right? So so if you zoom it up in a smaller one, so it will be something like, suppose this is xj and this is xj plus 1, and it will be something like this. And you need to find the area, this area, right? You need to find this area. So how to find this? Yeah. So this is again another integration, right? Isn't it? So this is again an integration to find this one. So I mean, you have this part and this part of the curve, and you integrate on this one, then what? So you reduce from a big one to a small one. Then what? Yeah, do you get it? So the point was to approximate. So the point was to approximate. So what I'll present this approximation procedure is due to Darbu. Uh, Later, after Riemann, whatever Riemann did, after that he came and gave this one. And later we'll again explain what Riemann did, just to recall the history. So he considered something like that, two rectangles. Do you see? This is a rectangle. This is one rectangle, and this one another rectangle. Right? So how do you get this in these two rectangle? So you of course, this base one side is this one x, this is xj plus 1, xj plus 1. So this part is xj plus 1 minus xj, right? And for this smaller rectangle, the height is mj, which is infimum of f on fx on xj minus 1, xj comma xj plus 1, right? So is this clear? So this part is infimum. So what will be the other part? So what is this length? What is this length?
Supremum.
Right. So you take supremum. So this is supremum of xj comma xj plus 1. So I should write it properly. This is supremum xj plus 1 of fx. We call it capital MJ. Okay. All right. So the area area under the curve one. This one is bounded by both sides. Here it is. Maybe I should move this one a little bit. This is mj times xj plus 1 minus xj, and this is by mj times xj plus 1 minus xj. All right. And this happens for all j from 1 to n, right? Is this clear, this part? So we divided this one by this partition. So this is, suppose this is xj and this is xj plus 1, and we zoom one up here. So this is the portion we are zooming. This one comes as this, right? And we get this area under curve on that small interval is bounded by small mj x minus xj minus xj plus 1 minus xj, and capital mj xj plus 1 minus xj. All right. So this is very important. This is the fundamental state to define integration. All right. Yeah. Is this fine? This is not difficult, right? It's very simple. Then what we do is, of course, you see area of this one. If you sum it up, you get the integration, as the classical definition of integration, which is area under the curve, right? So so we define this mj xj. There is one problem about notation, because we have started from 0. So this, excuse me, we have started from 0. So it would be better to call it uh, just a little bit of notation to make things proper. So this should be j minus 1 to j. So this would be j minus 1 to j, and this would be j minus 1, and this is again j minus 1 to j xj, and here also uh, xj minus 1 xj. Well, to get this summation proper. Yeah, so there is this one also, j minus 6j minus 1. This one, j minus 1 xj, and this one minus xj minus 1. J from 1, because it will then start from x0. Otherwise, it will not start from x0. It will start from x1, and which actually we have to so miss one interval. So this one, other things are same. So this we just look at let's look at this sum, small mj times this one. So this will be bound less or equal to the area under f, and this will be bounded by summation mj xj minus xj minus 1, j from 1 to n, j from 1 to n. Okay, so this summation, let's it so this one is depends on the partition. This also depends on partition, right? This also depends on partition. So therefore we name it. So define u pf to be this sum. Sorry, lpf to be this sum. J from 1 to n. P is the partition. Mj xj minus xj minus 1 and u pf to be j from 1 to n capital Mj xj minus xj minus 1. Alright, where P is, P is a partition. The partition x0 less than equal to x1 xn. So here it is a p. Okay. So this sum depends on partition. This is the all depends on partition. So now want to incorporate a limit of those. So in some way, see, we have kind of a sandwich type of stuff here, right? Area under F, which has no dependence of the partition, but in this case you have dependence of the partition. Here also you have dependence of the partition. So we should remove the dependence of the partition. All right. So how to do? To do is the way follows. So this one sometimes called. So this guys has a name. So this is lower sum of f of f for the partition P. So in short, lower sum, and this is called upper sum, right? L for lower sum actually. Now we need to go towards the limit. So how do you take the limit? Limit is as follows. So you look at supremum of LPF. So in the notes you make a correction here. So this one is supremum of LPF. In the notes it is written supremum of UPF. Okay, so that part you need to change. So this is supremum. Supremum were taken so over P. So the supremum is taken over all the partitions. All right. Is this fine now? And similarly, we will have this infimum of the right side. So infimum of the right side. So this is true for every partition, right? So see, this is interesting to note. Is so this one. So this is true for every partition P, every partition x naught less or equal to x1, so on, xn, b, right? So then, if you look at supremum, that will be less or equal to area, and if you look at infimum here, that will be greater or equal to area, and that is what we are looking at. Infimum of U, PF, infimum taken over all the partition, the infimum is taken over all the partitions of the interval AB, partitions of AB. And now again you give a name, this one integration fx dx, a to b, but then this one put a line here, so this is it, and this is called the lower integral, and again this one is as a to b upper fx dx, and this is called as upper, so the upper integral. All right, so upper integral or upper lower Riemann integral, here also Riemann integral. Now this is very interesting. Now this one, now one can define when a function integrable, Riemann integrable. So let me give the definition. A function f from a to b, we do not need continuity at all, is said to be Riemann integrable if integration a to b upper fx dx is equal to integration a to b lower fx dx. That is the upper and the lower Riemann integrals are the same. All right. So what do you mean by taking supremum and infimum here, right? So you look at all partition kind of stuff and you do, what does it mean? Actually, what comes out is actually you look at a partition, add some more points, add more and more points, more and more points, and as the number of points goes to infinity, you will get the integral. Right? So any question here in the definition? Any question? I'm done with this first lecture of Riemann integration. We'll talk more about what Riemann did next time, and yeah, the story will continue as well as the theory.
So could you just indicate like what was the notion of integration in use before Riemann?
Well, it was not precise. It was just so. For example, if you look at this one, we never used continuity anywhere, right? In the definition to define this one, that one, this, that, right? Nowhere continuity of f is used. We got it as a motivation. So previously they used to take functions to be sufficiently smooth so that you can calculate the area of this small region, and then the area under curve was that integration. That was the notion actually. So that comes actually that existed from Newton's.
So like you could only integrate continuous functions before Riemann.
Right. So there was no notion when something is integrable or not. There was no such notion. No such notion. Even continuity came, afterwards, right? So continuous function was kind of vague. It's just take a pen and you keep moving. That actually was kind of continuity, continuous curve. Or it will give you a graph which is whose curve of, of a function which is continuous.
So Weierstrass's continuity was also after Riemann integration was defined.
Exactly. Wester's integration, Wester's, this epsilon delta came around 1860, 70, something like that, after Riemann integration. So people have this concept of continuity. Differentiability was that limit was known from Newton. The existence of that limit, okay, that is fine, but it was not very clear which functions are differentiable and which are not. Those things, precise limit was not clear until Weierstrass. So most of people think that the series, the main point which was missing was convergence of infinite series of functions. So that part was missing. It came along Weierstrass. So that part there. So these things were vague. So people had a lot of debates on which function is, whether you can express any function, something like that. So yeah, those notions were not properly defined, and yeah. So here, what Riemann considered is to make sense of this kind of integration for a function which is not even continuous. Okay, so you can remove your pen, and if graph is not properly visible, then what you do, right? So Riemann defined this one, and then he had these things. And if you look at this infinitely many points here, so you will have infinite series both side, and you have this convergence, right? So one need the convergence of series to define this lower and upper integral. All right, and then this equality gives this one, and Riemann also gave. So that one, if some function, so what I said here, so if these functions will have this property, then it is integration makes sense. So that was Riemann's contribution, is actually give a large class of functions where integration exists. So for discontinuous function, people could not have thought much about this integration. But
Uh,
yes.
oh, okay, sir. And one more thing. So when we like Riemann integration in second semester, it was introduced using the notion of tagged partition. So so the one like the supremum, infimum one, and the tagged one, do they end up being equivalent? Slightly different notions of integration in general.
Right. So you look at a function and you look at f zeta and this xj minus one type of things, right?
Yeah, we had those partitions, and then we gave each partition, like each interval in the partition, a tag, and then on that basis,
Right. True. So that is what actually Riemann did. So the tagged partition stuff and all this, it comes like that, and this is equivalent with the upper and lower. So this, have you seen this one? This equivalence of this tagged partition is same as this.
No, sir, we didn't actually, I think, know what supremum and infimum were formally in second semester. So probably,
Okay.
yeah.
Yeah, but that is the reason he has to go with this tagged partition. Then you have infinite series, and concept of convergence of infinite series would give you the integration. All right. Then you can actually tag any point in the interval, and you can get the same limit. And then if you get that the same limit, then it will say this is integrable. But this can be visualized much easier way once you have the notion of supremum and infimum, and we'll show that this is equivalent with the tagged partition what we have learned in the second semester. Okay,
Okay, sir.
we'll show that. Yeah. Any other question? Yeah, all right then. So you have tutorials now. Problems from the okay, we'll see you next time. Okay.